bridging the gap between atmospheric science and grid modeling. And I'm very, very happy to have the cooperation of the Renewable Energy Committee of the American Meteorological Society in putting this session together. A number of people who assisted with that are here with us today, and for that, I thank you very much. The session will be chaired by Cathy Finley. Cathy, I met about 20 years ago when she was working for WindLogix with Mark Alstrom when we were doing some of the early wind integration studies. And I lost track of her for a while after she left WindLogix, but I started poking around and I found her at the University of North Dakota. So she came down from the university and agreed to chair the session this morning. So we're very glad to have her back. And Cathy, I'll turn it over to you.
Well, thank you so much, Charlie, and thank you for inviting me. As Charlie said, it's been a while since I've been at one of these, and this was always my favorite conference to go to when I worked in industry, because you're working on your own little piece of the puzzle, but this is where you get to see how it all comes together and the rubber hits the road. One thing that really amazed me is how much things have changed in what seems like a relatively short period of time. I guess it's been about 7 or 8 years since I've been at one of these. But what I found the most shocking was how rapidly our electric grid system needs to change in response to the increased load demand and in response to the amount of weather-driven renewables that need to come on the grid to meet that demand and our clean energy targets. And if all that wasn't complicated enough, we're also living in an age when our weather and climate is changing very rapidly. So I was really happy to see that the Renewable Energy Committee and AMS are involved in co-chairing this, because to meet some of those challenges and successfully navigate our way to our next version of our energy grid, we're going to need some cross-disciplinary collaboration. So we have some very interesting talks today lined up for you, more looking at things from the weather and climate perspective of some of the challenges that we're facing. And the session will be similar to the others in this conference, where we'll save all the questions for the end of the session. So if you have questions, please jot them down, and we'll have about 20 minutes at the end of the session for questions and discussion. So without further ado, I'd like to introduce our first speaker, Justin Sharp, who has recently transitioned to a research leadership position at EPRI.
Can you hear me? Great. Thanks for the introduction, Cathy. A little discombobulated here this morning. So, as Cathy just said, I've recently transitioned to a new role. It's essentially a bridge position, and it's a really good place for me to be at with where I'm at right now, because I think there's a lot of really important challenges that cross between the disciplines of power systems and atmospheric sciences. So I want to caveat the presentation today, and that I'm going to say some things that I feel quite strongly about. So these are my own opinions, not necessarily those of any of the people that funded the work or of EPRI, but I think for the most part, most people agree with me on a lot of the stuff. So I'm going to start off talking about why this subject of bridging the gap between atmospheric sciences and grid modeling, and the whole of the energy transition for that matter, is so important. Why it's so important to get really good weather and climate intelligence, what's currently missing. And it's more than just data. It's not just that we don't have the data we need. Like, engineers are clamoring and they're saying, I need data, I need data. It's not just about data, it's about intelligence. And that's what's I really want to make sure it's clear today. So then I'm going to have a quick report on current activity, and then give you my vision into a possible pathway to producing a sustainable, fit-for-purpose weather and climate intelligence data set. What's really important here is this is no longer just a research topic. We need to have a foundational infrastructure that provides us with the information that we need to connect the dots. And this is why. We have an evolving energy weather nexus. Many people in this room will have seen this figure over and over again. I really just want to emphasize that basically we're in a massive transition where the grid is becoming intensely weather dependent. Meteorology and climatology needs to fit hand in glove going forward into the future with the way the grid operates. We need to understand the weather impacts and the weather complexity and the way they're growing. Essentially, on the load side, as we transition to electrify everything, we're essentially driving around little mini residences that need to be climate controlled. That makes them weather dependent. So transportation, EVs, everything else is going basically all electric. Our commercial and residential spaces will be heated and cooled with electricity. Many industrial processes are also becoming electrified, although that has less weather dependency. On the generation side, the complexity just absolutely explodes. And I don't think people have really got their arms around this yet. A way that I've tried to explain this to people is if you have a fossil fuel plant, say a gas plant in one location, and you picked it up and literally just moved it 50 miles down the road, it would produce basically the same output. If you do that with a wind and solar plant, you get completely different characteristics of the plant, not just in how much it generates, but when it generates, how it ramps, everything changes about it. And so we need to have a really good understanding at a pretty high fidelity of the drivers of our generation in order to produce an efficient grid that works. So I posit that our weather intelligence right now is inadequate. I don't just think it's minorly inadequate, I think it's very inadequate. We have basically a situation where the users only vaguely touch the, let me see if my pointer works, where users are basically only just at a small interface with the folks who are producing the data. There are amazing data sets out there, don't get me wrong. We have some really good weather intelligence, but it's not really at the resolution or fit for the purpose to for general power systems use. It needs a lot of interpretation as well. So we've got folks who are handing data down and we've got folks that are using data. We have a giant gap in between. And this is kind of what my vision is for where we need to go. We need much more vision, investment, and leadership into this process, not just a quick research project to produce a data set, but an ongoing sector-specific R&D methodology that has a feedback loop, that has strong connections between the folks who need to use the data and the folks who are producing it, and that is managed and orchestrated. Right now, I kind of use the analogy on in the data tutorial on Tuesday. I feel like we have an orchestra all playing amazing instruments and everything, but nobody's conducting. And the folks who are listening aren't able to necessarily tune into the frequencies that are going on. In addition, we need a bunch of other stuff that is not there at all right now. So we're going to go through them really quickly. Ground truth data is present. We do have all these wind and solar projects that are being built out that are creating this amazing ground truth data set with which we can validate these gridded weather data sets. And what's really important, by the way, and I haven't mentioned this yet, but it's really important to understand that the data that we're using is not observations. It's not data that we've taken measurements of and then put into a database. It's synthetic data. It's been produced by models. Models are never perfect, but they can be useful if we understand the level of uncertainty and the biases within the model. And that requires ground truth data. In the world of AI, the ground truth data is even more important for being able to improve these data sets. So we need a validation process. And we need a curation process so that people can understand the data that they're using and apply it in appropriate ways. Right now, there is a lot of data out there that has been misapplied and potentially maybe resulting in us missing the mark by a significant amount with respect to our conclusions about how well we can do a weather-driven system or what the right way is to do it. So that kind of all brings me to this cartoon. Which I think is fairly fitting for where we're at right now, where Dilbert says basically that all his data is inaccurate and that he needs data to perform analysis. And if we can concentrate hard enough, then we can pretend that it's all good enough and that it all works. And that is just a recipe for disaster. And I feel that's kind of where we're at. So where are we right now? So I've been involved in this work for a couple of years, been doing work with ESIG. I led the ESIG task force on weather inputs for the power system. That report has received a lot of really positive attention. I've been very fortunate in that I've had Grid Lab really help fund me do a lot of socialization and outreach activities around that. And it's getting a lot of traction. And I feel like folks at the RTO level and at the utility level are really starting to get what this need is. And I feel like DOE's listening. NOAA's certainly engaged. You know, this has been the subject of this meeting. We've had some recent meetings. IEA is starting to get involved. There's a lot of people who are really starting to coalesce around the importance of this at this time. So I think we're in a moment where we could do something really positive. But I think it's really important that we look at the full picture. There was a brief sprint, and that's worth mentioning, in December, where there was some GRIP funding that came out with, you know, $1 billion worth of funding for infrastructure projects. And unfortunately, I didn't really have my ducks in a row to be able to get a team together to potentially apply for that type of funding. But that's the type of level of funding we need. It's in the millions of dollars. It's not a few $100,000 or a $2 million project. It's an ongoing project that's going to take tens of millions of dollars, and I'll go through the numbers a little bit more in a moment. So I wanted to look at a proposed methodologically agnostic approach to this. And if you want to look at the methodologies for producing data and things, the tutorial from Tuesday, which was all recorded, laid out a lot of that in quite a lot of detail. So you go review that. But this is my overall big picture, and I'm going to step through each of these components, and hopefully it will become a little bit clearer. So you have a selection process, basically, where you're trying to define who's going to produce the data. And it doesn't have to be one producer. It could be multiple producers. The whole process needs to be managed by a managing entity that has the view of the industry in mind. It's not just, oh, I think I understand the data you need. Here, let me go and produce it. Here it is. Go use it. There needs to be an entity that is taking the requirements from industry, that understands industry well, and then can manage and coordinate and orchestrate this whole process. I happen to believe that an organization like EPRI is the right place for that, and that was actually one of my motivations for why I've landed where I have recently. There needs to be a funding agency, obviously. Given that this stuff is a common good and that it is much bigger than any small organizations can really handle, I think that naturally belongs with perhaps the government, but probably also with some public-private partnership so that the industry itself has some skin in the game as well. So going back to the selection process, basically, an idea I had would be to have a data producer selection competition where basically there's an RFP put out with some reasonable amount of funding to gather producers who can produce these atmospheric data sets together and do a very, very detailed validation of the data sets that are produced for say a year or something like that. And what we would really want to do there would be really try and gather as much atmospheric data from wind and solar plants as we possibly could to do that validation. Now, if the wind and the solar industry is not ready yet to be able to collaborate and coordinate and doesn't understand that, you know, with the way I view each one of those wind and solar plants is they're a jigsaw piece into our vision into what the atmosphere looks like and how it's behaving, and they're collecting that data. If the jigsaw puzzle pieces are scattered around the room, we can't see the big picture. But if we can get all that data into one place, we can start to see that big picture and it'll start to coalesce. But anyway, that was sort of an aside around the need to get some data transparency. But at a minimum, ERCOT is already doing this. So we can use ERCOT's data to do a really detailed validation. It would only be for one region, but I'm sure we could probably find entities that would cooperate to be able to do a really detailed validation in some other regions. But the key here is validation. Producing data for data's sake is just throwing more money down the drain. So that's where you have your validation entity comes in. They are doing this detailed validation. We come up with and entities that seem to be able to produce a data set that's better than what we've got available today. If we can't produce anything better than what we've got available today, and that should be part of this process, by the way, is to compare it with what's available today, particularly things like the 404 and the Wind Toolkit and ERA5, to see what the best we can do compares with what's out there today. That gives you a synthetic data producer. That producer then starts building a data set back to a period such as probably 1990, 1980. I'm concerned about going any further back because at that point, the data that's available to the atmospheric data that's being collected that's available to do the synthesis is actually fairly limited because we didn't have satellites. And so the beginning of the satellite era is probably where I think we should go back to, but that would give us a long enough data set to be able to capture most of the tails. Now, at that point, you finished with your data selection competition. You start producing your synthetic data. That goes through the validation entity. And note that validation entity is not the same as the people who produced it. We have this natural tendency in our business right now to go out and produce data sets, and then we do a validation, and it's the same entity doing the validation as producing the data. And I'm not saying there's anything nefarious going on there. It's just, if you're doing a validation, the purpose of the validation should be to expose the flaws, not to show how good the data is. And it's really obvious when you think about it, but that's not how we've been doing things. So then the validator produces validation reports and validation tuning data that are available to the end user. And then the next step that's missing, and this is the really big missing piece right now, is what I've called a curation entity, which is the interface to the end users. So that interface basically provides the data archive, the ability to provision the data, not just the synthetic data, but the validation data that goes with it and the tuning data. They provide user education and advice, and they manage the feedback loop to the managing entity to understand what the end user's needs are, how the users are using the data, make sure that this orchestra is making a beautiful, harmonious piece of music. And then when you've got all that, the last piece that you need to do is science is always advancing. And so you need to do a periodic refresh of that whole process so that when we say, okay, we can produce a synthetic data set that's 20% better than we used to be able to, when it makes sense, and bear in mind, there are trillions of dollars on the line here. The transition is trillions of dollars. When it makes sense to spend another $10 million or $20 million to refresh the entire data set, let's go ahead and do it. But the point being here is this is a framework and an infrastructure for an ongoing process. It's not a project that produces some data and then we shut it down and hand off the data and say we're done. It is an ongoing process because meteorology, climatology, and the energy grid now fit hand in glove with one another, and they need ongoing support. So that's my vision. How much will it cost? How long will it take? These are very rough numbers, but I didn't want to just say there's a problem. I want to say there's a problem, there's a solution, and here's an idea of how much it's going to cost. So worst case scenario is I'm thinking, if we were to map the entire of CONUS at 1 kilometer, and whether it's 1 kilometer, that's a science question that we need to answer. 2 kilometers may be the best number. But going back to 1990, which is what I'm suggesting, or perhaps 1980, again, science question we need to answer, extended continually to 2035. And we need to go beyond that, but I needed to end it somewhere. Otherwise, the number's infinite, right? So you have the multi-vendor competition phase. I'm thinking probably on the order of $2 to $3 million. If we do it properly, we do a really comprehensive validation. Data set production, initial $8 to $15 million, the ongoing annual production, $1 to $2 million. I have tried to be relatively conservative here. The dissemination and the management and all the rest of that are numbers that are, compared with what we're spending right now, these are rounding errors. The validation and uncertainty quantification is really important, though. And that's the part that's actually difficult to quantify right now, because if we can't get the industry to actually provide all the data and provide data transparency, that process is going to always be hampered and always be difficult. And so that comes to really a regulatory issue, that a condition of interconnect, in my opinion, should be that every single renewable entity that interconnects onto the grid gives transparency to its data. Now, it can be under an NDA, it can be embargoed. I'm okay with any of that stuff, but I will say that if we are going to understand this jigsaw puzzle, we need the pieces. The total here is, $30 to $70 million. This is not big money, but it is big money compared with what's been spent for the last 10 years or so. The project time is only about 1.5 years to really get the initial data set, and then ongoing, we can refresh it every month, just like ERA 5 is refreshed every month. A detailed cost-benefit analysis is really needed to establish that the value of that observational network and the value of everything in general. I believe in this vision, but I'm also willing to be proven that it's not worth spending this amount of money. But in the AI world, the quality of the ground truth data will be absolute king. If we can get really good, high-quality data, not just that you interconnect and you provide data, you provide good quality data. I think we can really make a big difference here. So I do see that I've actually got a couple of minutes left, which is great. I timed it right. I wanted to make a quick word about climate change. It's a really important topic to electric utility planning and operations. I think often it is eclipsed the fact that we don't understand enough about our climate variability right now. We're going into a world where our generation is defined by weather and climate and by the climate variability within that. Now, of course, that is changing, but until we get our arms around the baseline, how can we understand how it's changing? So the number one priority is to actually get the history right. And then from that, if we're extending it ongoing, not just doing 7 years like the wind toolkit or even 40 years, but if we're extending it ongoing, we start to see those trends. And implicitly address them. And we can validate and begin to quantify the uncertainty of the other models that are being used for climate change. So this sort of fits in and gives us the foundation that we need. So that's my pitch for why we need to do this. I hope it's relatively clear. I'll hand it over to the next speaker. Thanks.
Great. Thanks so much, Justin. That's quite interesting, and I'm guessing it's going to generate a lot of discussion, which is great. Our next speaker is John Jensen. He's currently an engineer in the Reliability Modeling Group at WECC.
All right. Okay. Perfect. Well, thanks everyone. Thanks, Cathy, for the introduction. Like Cathy mentioned, I'm John Jensen with WECC. I work in the Reliability Modeling Department. I'm going to talk today a little bit about some of the modeling we've been doing with extreme events in the Western Interconnection. So with our latest 2023 study program, that's the latest study program that we finished at WECC. Here's a few studies that we've been involved with looking at extreme weather and the year 10 and year 20 futures. So we have our year 10 extreme cold weather event, and this was a production cost model, and the year 10 was 2032. Then we have a year 20 extreme cold event, which the year was 2042, another production cost model. And then we do have a year 20 extreme heat event, along with our year 20 foundational case, which acted as the reference case for these other two year 20 extreme weather event cases. And then just something to be aware of as well. The year 10 extreme cold event and the year 20 extreme cold event were based off the same cold weather assumptions. So we were able to compare those, and I'll just hint on those a little bit later. And for this presentation, I'll mainly be focused on our year 20 extreme cold event and kind of what we did there. I'll talk through our approach, process, challenges, questions we had along the way, and so forth. So for scoping and approach, what we wanted to do is kind of figure out like, what are the reliability risks or vulnerabilities on the system due to extreme cold weather in year 20? And it brought a lot of questions as far as what that exactly looked like and what we wanted to look for. But as far as vulnerabilities, we were mainly concerned with what level of extreme cold or load would we start to see vulnerabilities, like unserved load, for example. Also, what areas of the Western Interconnection are more susceptible to these risks? Also, what durations do we start to see signs of unserved load and things like that? We're also interested how energy storage would be affected, but then also how are resources affected, how generators are affected by this extreme cold, and then how loads change as well. But we did have a few questions and challenges along the way. Number one, what does the year 20 look like, or what could it look like? So that's a big question that we had. Another one was, what does an extreme scenario look like? We had quite a few questions regarding this. Do we just say it's, how extreme do we go and stay in the realm of realistic? Do we say it's negative 400 degrees everywhere? That'd be very cold, very extreme, but maybe not realistic. So we had to do our best with that. And then also, what data was available? What tools or resources did we have? And then how do we put that in a power system model? So step one, I guess, for our year 20 look, what does year 20 look like? So we decided our year 20 was 2042. And what we did was we started with our year 10 anchor data set production cost model case. And that was built out to 2032. So we just had to forecast that another 10 years past that. And we decided to start with our 2032 anchor data set because that was our solid year 10 case that we had. It's a stakeholder vetted production cost model. A lot of the data comes through the loads and resources data collection process, and which has reporting responsibility through NERC, supporting Mod 32. And it's used in a lot of different ways. For instance, the Western Assessment of Resource Adequacy, of course, our year 10 anchor data set production cost model, along with a long-term reliability assessment and the state of the interconnection report. It's just, the LNR data is used in a lot of things, and it's vetted. It goes through a lot of review. So we decided to start with this. And then what did we do to get from year 10 to year 20? We did our best to project, and we didn't want to, we weren't trying to forecast the exact year 20, because we all know that there's, so many different possibilities of what that could look like. But we mainly wanted to focus on, we just want a business as usual case that we can use as a reference case for when we build our extreme weather case on top of that. So we use a linear annual growth rate. We took year 2025 and took a trend line out to 2032, and then just forecast that or push that out another 10 years to get 2042. And then for generation, we did our best to try and keep the same capacity margins as we did in our 2032 case, and just push that out to 2042. So our capacity margin, we compared the capacity in each area to the peak load in each area. So we just tried to keep that going forward to 10 years. And the resources we added to the case were mainly wind, solar, and batteries. And we distributed them by area rather than putting them on specific buses, since we didn't know exactly where those resources would be and on which exact buses they would be. And then, of course, once we did this, we benchmarked it with some other year 20 cases that are out there. So for instance, the NREL 2022 standard scenarios, a lot of information, 2040, 2045-ish. In there, we compared it to those cases. We also looked at the EIA annual energy outlook. And then there's also another case that WECC did a while ago called the WECC long duration energy storage assessment. And that was the year 2040 case. So we looked at our loads, capacity, and compared it and benchmarked it to those. And we thought, hey, it's actually pretty close. Let's go with this. One thing to note is we did not change the transmission from 10 to year 20. We didn't want to project or put in any candidate lines. So we stayed with the transmission that was in the year 10 anchor data set. Another thing we did is we just let retirements retire naturally. We didn't expedite any retirements due to like coal or natural gas or anything. So they would just retire naturally when the time came. Then the next question we had was weather assumptions. So what does a realistic cold weather event look like? Like I mentioned, is it, negative 100 degrees everywhere the whole year? That'd be very extreme. Probably not. So what we did is, luckily with the help of PNNL through our advisory group, they were able to inform us on what a realistic extreme cold weather event would look like, what parts of the system are affected, how long, duration, what areas, what temperatures could possibly be hit. Also how wind and solar resources are affected, how gas resources are affected, thermal in general. So that was a big help. And then we thought about how we could put this into our model so we could, increase load due to colder temperatures or hotter if you're doing extreme heat case, decrease generation output due to the effects of cold on the system, and then also increase forced outage rates as well. So these were kind of the considerations we took in this study. So what we set out to do, what we decided to do in the end was we decided to mimic a historic event and then make it more extreme until we saw signs of unserved load. So we decided to mimic the Winter Storm Elliott, and Winter Storm Elliott, it happened in December 2022, around December 20th, 21st through the 26th of December 2022. And as you can see, there's some pretty cold temperatures. I don't know if the laser is working, but negative 38 in Butte, Montana, Casper, Wyoming, negative 42, Denver, negative 18, Edmonton, Alberta, negative 40, Pullman, Washington, negative 20. So pretty cold temperatures that stayed cold for quite a while. So we thought this would be a good one to mimic and then make more extreme. So first things first with the loads, that's the first challenge we tackled. And what we decided to do was we took the historic Winter Storm Elliott load from 2022 and then push it out and implement 2042 energy. So basically we took that same shape from 2022 and built it out to 2042 energy. So because we wanted to keep that shape, but push it out to 2042. So that's what we decided to do. And then to make it more extreme, we decided to add a 10% adder, which is that red trace on top. So the gray trace is the historic 2022 load. And then that tannish, goldish trace is the 2022 load pushed out to 2042 energies. And then that red trace that overlaps, it's that 2022 shape pushed out to 2042 energies plus an additional 10% of load growth. And we phased in and out that load growth starting about the 19th of December and then phasing it out about the 24th. So 10% load adder just to make it more extreme. Another thing that we did is we looked at wind and solar and we thought, what would be kind of like the worst case scenario for wind and solar outputs and profiles? So we looked at our December profiles for wind and solar, which we use for our anchor data set, our 2032 anchor data set, and it's based off of a reference year of 2018 as our weather year. So we looked at that for December, and the lowest wind and solar output for wind and solar combined was on December 6th. So what we did is we shifted December 6th over to right in the middle of this Winter Storm Elliott cold snap, so about the 21st, to just make it more extreme as well and say worst case scenario with wind and solar, say there's low wind, low solar that day. We'll see what happens. Then forced outage rate. We did some research and we studied the Texas event, Winter Storm Uri, and we saw that the forced outage rates for Winter Storm Uri, they hit 3 times greater than normal. And so for the Western Interconnection, we're more used to cold weather, right? Like we get pretty good winters, especially in the northwestern part. So we decided that probably equipment would be winterized a little bit more here than it was in Texas. So we thought doubling forced outage rate would be a good assumption for the study. And then natural gas rates, derates, for example. We decided to derate some natural gas generation, and we started it on December 19th and then ended it on December 23rd. So we phase it in, phase it out. And we did it for all the northern regions within the Western Interconnection. We also ended up derating California, even though California is warmer than like the northern parts of the Western Interconnection. It does use the same natural gas pipeline infrastructure, so it would be affected. So we decided to derate California natural gas as well, but to a lesser degree. And it's usually about half, or pretty much half of our other derates. So we did it 15% natural gas derate, and then California was 7.5, 25% natural gas derate. California was 10, then 35% natural gas derate, and then California we derated to 17.5, so about half. So that's like our approach or assumptions that went into it, and then I'll get into the results a little bit too, kind of show you what happened when we ran this study. So here is our unserved load, and when we started seeing unserved load. So we ran a lot of cases, as you can see here in the graph. The very, very left bar, which is 0, is the 2042 foundational case. This was the reference case, so no cold weather impacts applied to this at all. So 0 unserved load, that's what we started with. And what we noticed is as we applied one impact at a time, everything seemed okay. So we took our reference case, applied double forced outage rates, everything seemed okay, no unserved load. And then as we took our reference case and applied the low wind and solar shapes, everything seemed okay, this next one. And then as we took our reference case and applied the December Winter Storm Elliott loads out to 2042 energies, everything seemed okay as well. But once we started compounding more than one extreme cold weather impact, that's where we started seeing unserved load in the year 20 future. So this next one, we're going to see 76 gigawatt hours of unserved load. That's where we compounded the low wind shapes and the December Winter Storm Elliott load out to 2042 energies. And then beyond that, as you compound more and more, you get more and more unserved load. So the next one we compounded the December loads plus that 10% increase in load. And that's where we get the 113 gigawatt hours of unserved load. Then the next one, low wind shapes plus the 2 times forced outage rate to get the 248 gigawatt hours of unserved load. And then beyond that, with our other cold weather impacts, you just get more and more unserved load. We get into our derate cases, but this one right here, this 2042 EC, this is the case that has most of the impacts applied to it. So for instance, it has the Winter Storm Elliott loads, it has the 10% adder, the forced outage rate, and the low wind and solar shapes. And you might be thinking to yourself, why did you go this far? Why didn't you stop here? You already know you have unserved load, like you already know that if you add more impacts, you're going to get more and more unserved load. And that's what I want to mention here today as well, is we did this year 20 study in combination with the year 10 study. So the year 10 study, they put all these same impacts in for their case, and they started with the year 2032 anchor data set and built upon that, and then put in all of these other impacts that I mentioned. And so they got to hear their extreme cold, where they put in forced outage rates, low wind and solar, the 10% adder, the winter storm them in there. And then they got to here and they said, oh, still no unserved load. So then they started derating the case, 5, 10, 15%. And the 15% natural gas derate with all the other cold weather impacts applied as well is when they first started seeing unserved load. So that's right here, this one right here. So year 10 started seeing unserved load here. Year 20, we started seeing unserved load here. So moral of the story, year 20, according to our analysis, seems to be a little more sensitive to these extreme cold events versus year 10, and basically due to the makeup of the year 20 future, our business as usual year 20 future with extreme cold impacts compounded on top of that with more renewable resources and fewer thermal resources. Other things we look at, this is an overview of that whole week-long cold event. We have our generation stack of resources, and then that line on top is the load, and then that dotted line or that dotted trace, the gray trace at the bottom is unserved load. But any time where you see that load line at the top in black, if you see white under there, that means that there's unserved load because the resource stack can't reach that load. So obviously, this is like the peak of our extreme cold weather event. Around the 21st, we saw quite a bit of unserved load around there. So it's just a week-long view of the whole event. You can see the cold event kind of ramping up and then ramps down a little bit. Other things we look at are net regional transfers. This is net, so keep in mind pluses and minuses. But the left chart left graph, I guess, so to speak, is our 2042 foundational case, our reference case. The one on the right is our extreme cold case with a 15% natural gas D rate. You do see some trends in this. You see a lot of the flows trying to go north to sort of mitigate some of the unserved load up here, or shortages up here in the Northwest, which was hit the hardest because of the load pockets, and it was modeled as more extreme on the cold side for our extreme cold case. So you see a lot of flows increasing going north to the Northwest. For instance, California, Mexico to Northwest goes from 228 north to south to 1649 south to north, and some of these others going north as well. One thing we noticed too with energy storage in our case, and this is kind of an artifact of the software which we use, which was GridView. The energy storage would only cycle over 1 day period, so over a 24-hour period. So it wouldn't really cycle over multiple days, which we were kind of hoping it would to help mitigate some of the unserved load later on in the week, especially with that look-ahead logic. So every day kind of looked the same for unserved load. Charge in the midday and then discharge in the evening, which is pretty normal, but we were hoping it would maybe hang on to some of the storage for some of those really rough days or those high load days. Another anomaly that we saw is if you look at hour 1, this is just due to the nature of the program. It would always start charging in hour 1, which would contribute to unserved load for hour 1, and then it would mellow out. So they're currently working on a better model for multiple day cycling for energy storage, so we can run more of these studies. Another look at transmission. We see this is an hourly snapshot of the whole year. Here's COI, California, Oregon interconnection. We see a lot of the flows changing from north to south to north. Looking at the reference case in blue and the extreme cold case in red. We see a lot more going, or the extreme cold case in blue and the reference case in red, sorry. But we see a lot more south to north flows, which I showed previously. A big thanks to all of our contributors as well in this, and feel free to click on the reports. The links are in that first slide I showed to read the full description of all of these different weather events. But a big thanks to our contributors, the year 10 and year 20 extreme cold weather event advisory groups, which helped led and guided a lot of these studies. A big help to EPRI, PNNL, and others on the expertise that they have given to us for all of these studies. I do want to mention some other WECC other weather involvement at WECC that WECC's currently looking into. Not so much in the reliability modeling department, but other departments, the situational awareness and operations analysis departments at WECC. They put together a probabilistic planning for tail risk report through the performance analysis work group. They've created a white paper on that, and then also situational awareness and operational analysis. They've developed a wildfire dashboard, wildfire season outlook report, and then they're also doing investigations on Winter Storm Uri and Winter Storm Elliott, and then also Winter Storm Jerry and Winter Storm Heather. I'm doing an inquiry on those. So we're looking at weather as much as we can. It's definitely a hot topic, and then especially in these different futures or different forecasts of year 10 and year 20. So for more information on these, feel free to click on the links in the slide, and feel free to read the full reports on those. So I'd just like to share that with all of you today. So thank you.
Well, thank you very much, John. That was a really interesting case study on how extreme event might affect grid operations in the future. Our next speaker is Jared Lee. He's a project scientist at the National Center for Atmospheric Research.
All right, so good morning, everyone. Like Charlie mentioned at the start, the session is co-sponsored by the AMS Energy Committee and Renewable Energy Committee. I'm one of the co-chairs of the Energy Committee, so I'm grateful to Charlie for being receptive for our proposal to help sponsor this session, and I do hope that AMS and ESIG can continue to partner and collaborate with each other more in the future, because we are all on the same team. We all want to see this energy transition happen. And so for this talk, I'm going to be overviewing what are some recent studies, more focused over the US, because I had to constrain it a little bit for time reasons. There are a lot of other studies looking at how climate change is going to impact wind and solar resources in other parts of the world, but for here, I'm just looking at studies for the US, mainly over the past 8 years or so. So the first study that I'm looking at here is Haupt et al. 2016, led by Sue, here in the second row. And so in this study, they looked at 50-kilometer grid spacing regional climate model data around mid-century for the whole US. They compared it to historical climate reanalysis data sets at 35-kilometer grid spacing. And they used self-organizing maps to look at what are the different patterns that are in both the current climate and the future climate. How are those patterns changing? And they calculated what the basically what the net change in wind speed or solar irradiance would be in each of these little subregions in NREL's REEDS model. And so basically the bottom line is that by mid-century, there are going to be changes in wind and solar resource, but for the most part, they tend to stay within about plus minus 10%. So here on the left, we have changes in regional mean wind speed, and on the right is for solar radiation. We have it for each of the different seasons. So for instance, in summer for solar, it seems to be that there's a general slight increase in solar irradiance across pretty much the whole country. But then for wind, in the southern US, suggestions of an increase in wind resource, but then a decrease in wind resource across the north. But then if we look at spring, pretty much in this study, pretty much everywhere a decrease in wind resource availability. But then in the fall, it's really hitting the East Coast hard. So really, there's a lot of heterogeneity here in both where there are going to be, or where there are projected to be increases or decreases of wind or solar resource availability. And that also changes through seasons and also diurnally. So there are a lot of things to pay attention to. The next study I'll look at is Craig et al. And also add, if you look through the recordings of this later, I have the citations and the DOI link for each of these studies, so you can go find them yourself. So Craig et al. In 2018, this is really a literature review of studies to this point, and they looked at what are the different component level impacts in the power system, and also they evaluated what's the agreement among the studies, what's the quality of the evidence, and what's the confidence in their evaluation. And then they also looked at what are some of the implications for power system planning and operations. So for instance, for demand, there's high confidence and robust evidence that demand is going to increase. And I think we all see that, especially with data centers, as we've seen over the last couple of days here. But then for transmission, only medium confidence that there will be reduced transmission capacity during peak demand periods. I'm not going to read everything here, but I'll zoom in a little more on wind and solar. So for wind energy resource, low confidence in decreased wind resources on average across the US. And as we saw from the Haupt et al. Study, that was regionally varying, but they have medium confidence that there will be heterogeneity in these wind resource changes across the US. And then for solar, they also found that there would be large regional and temporal heterogeneity in these resource changes. But they also found with low to medium confidence that there would be decreased solar PV resource in California. Now that's a bit contrary to what Haupt et al. Found, but they also saw that there would be increased solar resource across the Southeast. So different studies come out with some different results. And again, this is more of a synthesis of studies to date in 2018. And they also kind of helpfully put this all together in a sample day, kind of showing with the increased thermal curtailments under climate change, reduced hydro generation potential, reduced wind resources, reduced solar resources, but increased load, that there could be shortfalls that have to be made up. So this is a really interesting study to look at. Now moving ahead to Pryor et al. 2020, Sarah Pryor at Cornell University. This is also another really helpful review article that looks at dozens of studies evaluating wind energy resource changes worldwide, so not just the US. But they also ran WRF at 12-kilometer grid spacing driven by MPI or Max Planck Institute climate model boundary conditions. And they found that mean wind energy density, they found that it's likely to increase over the southern plains, but decrease over much of the northern and western US. And this is in partial agreement, partial disagreement with prior studies to this point. And that's kind of a theme. There are some things that are the same, some things that are a bit different. But they also have these really helpful tables in this particular paper. I'm only including the part of the table that's for North America. They have these same tables for every continent, showing what the different studies are, what the different variables are. Some look at wind speed, some look at wind energy density, some look at capacity factor, some look at annual energy production. Summarizing what are the different models and grid resolutions that are used, and what are the projected changes over what time period. So again, consistent with helped at all, most of these changes are within plus minus 10%, it seems. Like for instance, this particular study here, 2 to 3% increase over Kansas, 1 to 2% decrease in central Colorado. This particular study up to a 5 to 10% increase in winter, but declines in summer. So there are a lot of different studies that are, they're different in some of the details, but overall the changes seem to be fairly modest, which hopefully is a comfort. So then moving on, another study, Losada Carreño et al. 2020, their study was limited to Texas, using 1995 to 2005 as a reference in the 2040s as their future period. And they found, so these two graphics are looking at solar capacity factor and then wind capacity factor on the right. So for the solar capacity factor, mostly increases in solar capacity factor across all of Texas, and these 5 different climate models that they looked at were generally in agreement. Increase in this capacity factor over the southern, and then some disagreement in the panhandle. And then for wind, basically, they found that in southern Texas, these different climate models were decreasing the wind capacity factor, but then in central Texas, increasing. So a lot of very important regional differences to take into account. But again, these changes are generally 1 to 3%, so they aren't huge, at least for the wind, the changes in wind capacity factor. But like Justin mentioned, we also need to look and be concerned about changes in variability. So in this case, looking at extreme hourly variability, or the 95th percentile of the hourly variability. And for solar, all the climate models agreed statewide that this extreme hourly variability is set to decrease. And then for wind, mostly decrease across the southern parts, but then once you get into northern Texas and the panhandle, potentially an increase in the wind variability. So again, it's not just the mean resource that we need to be concerned about. We need to look at the variability and how that's going to change. Moving forward to now just last year, prior at all 2023, examining the probability of wind drought and bonus periods in different regions in the eastern 2/3 of the US. So they had data from 19 wind farms. And so they used WRF at 12-kilometer grid spacing, also driven by the MPI climate model at a high RCP forcing. So most of the wind farms, the capacity factor variability in the 2040s was consistent with the capacity factor variability that we see now. But the other 5 farms all saw decreases in the capacity factor variability. And for these different regions, so each line here represents a different wind farm in that region. So in the northern Great Plains, as we go to the 2040s, there's a suggestion of an increase in the probability of wind droughts, and also a simultaneous decrease in the probability of wind bonus periods. But then for the other 3 regions, there's really no trend at all, at least out through the 2040s. But even for the northern Great Plains, very sensitive here, even for the northern Great Plains, this increase in drought probability and decrease in bonus probability, it's still within the envelope of current interannual variability. So we can't really draw huge conclusions from this data set. And this was dynamic downscaling. So then part 2 of the study was Coburn and Pryor, and they used statistical downscaling. So because they used statistical downscaling, they were able to look at all of the US and not just mid-century, but also late century. And so this kind of summarizes here what the different colors correspond to. Are there decreases, which is red, increases, which is blue, or in yellow, it spans 0. So basically in the left column for each of these regions is for the 2040s and 2050s. The right column is for 2080s, 2090s, late century. So basically for mid-century, small differences of inconsistent sign, although generally some slight decreases in wind capacity factor. This is mean annual capacity factor. But then by late century is when we see some bigger changes and more negative. Although the one exception is up here in Northwest Coast, so mostly like British Columbia, Alberta. But there's only one wind farm in this entire region that they analyzed. So I think sample size issues kind of limit how strongly we can take conclusions from here that there will be an increase in that region when there are decreases predicted everywhere else. So also there's another study led by Melissa Bukovsky now at the University of Wyoming, and then with a bunch of my collaborators or coworkers at NSF NCAR, looking at how is the offshore wind resource going to change off of the West Coast with two offshore wind lease areas near Humboldt and Morro Bay. And this region, especially in the summer, is characterized by marine stratocumulus clouds and a low-level jet. And those dynamically impact each other in important ways for wind energy. So we want to know, are these marine stratocumulus clouds going to stick around? Are they going to get, basically, how is it going to change, if at all? And how is that going to impact the low-level jet that sets up, which in turn is going to impact offshore wind generation? And basically, what they found is with the HADGEM2 and GFDL models, they're both predicting a strengthening of the low-level jet over Northern California, but then around Morro Bay, basically no change, at least certainly not any significant change, with a weak decrease in wind speed. So this paper is submitted and in review, and there's a lot more really interesting detail about how the low-level jets will change that I am not getting into here right now. And so I'm also interested in how how all these studies have contributed, because there's a project that I'm working on right now. It's funded by NSF, by their cybersecurity or cyber infrastructure office, rather. The project's led by Cornell, and what we're doing is we're building basically an integrated framework of containers for WRF, for validation using the MET+ tools that are developed at NSF NCAR, and also visualization, really integrating those together so that we can lower the bar for access, particularly for grad students or for researchers, who basically making it easier to use these models and validation to do interesting science questions. And so one of the science use cases that we're demonstrating this on will be to investigate climate change impacts on wind and solar resources. We are interested in better quantifying the variability and the change in the frequency of occurrence or the intensity of extended or 1 to 3 month periods of both wind and solar drought and bonus periods. And most of the studies that I've shown earlier, the highest or the finest grid spacing that they got down to is about 12 kilometers. And for regional climate, that is pretty fine grid spacing. We're aiming to go down to 4 kilometers for CONUS, downscaling MPI climate simulations, and we're targeting a 40-year period, but validating the first 10 years of that with the MET+ framework. That's the plan. It's dependent on getting approved for large amounts of computing resources. So maybe next year I'll have something to update here, but I'm working on that with Sarah Pryor and Sue Haupt as well. So just in summary, most of the studies that we've seen so far in the US indicate changes by mid-century, even late century. Changes in wind and solar resource are generally plus minus 10%. But there's a lot of heterogeneity in that regionally, seasonally, diurnally. And so we need to pay attention to those issues. And so to be most useful, climate projections really do need to include information on variability at multiple temporal and spatial scales. Again, it's not just the mean resource, it's not just the mean error like John Zach has been talking about, but we need to care about the variability here too. And also just a word of caution, most climate models, global climate models, are run at grid spacings of about 100 kilometers, maybe a little finer than that now, but at 100-kilometer grid spacing, and I believe Justin showed this during the tutorial on Tuesday, at 100-kilometer grid spacing, the Rocky Mountains are basically a shallow ridge. And so at that point, you aren't getting, the climate model then is not simulating correctly the synoptic patterns, the Lee cyclogenesis in the cyclogenesis or formation of low pressure systems in the lee of the Rocky Mountains. And so you aren't getting precipitation patterns right, you aren't getting wind speed right, you aren't getting clouds right. And so really you do have to downscale the climate models, whether it's dynamically or statistically. And really to get at farm level estimates, you need really high resolution model simulations at cloud resolving scales. So I'll continue banging the drum that Justin loves to hit. And I also helped out with that weather data sets report as well. But really, we do need to have, it's critically important to have physically consistent, high resolution databases of irradiance, temperature, wind speed, humidity, precipitation, the whole ball of wax in both current and future climate in order to do whole energy system modeling and coordinated planning well. With that, thank you.
Well, thank you very much, Jared. This is a really important topic, and I predict there's going to be a lot of demand for your containers. Our final speaker of the session is Jennifer Newman. She's the Vice President for Atmospheric Science Research at REsurety.
All right, great to be here. This is my first ESIG meeting, but I've been to the AMS meeting many times in the past. So it's great to see this intersection between the meteorology and the grid communities because it's so important to get these sectors talking to each other. So I'm going to talk about forecasting tail events and their impact on energy price. And a lot of my examples are going to be for ERCOT because ERCOT is kind of a test bed for these really high prices. So I'm going to start with just a high-level overview of REsurety and how we forecast power prices, because that'll kind of give the lens to how we're thinking about these tail events. I'll talk about how extreme weather impacts power prices. And then the bulk of the presentation will be the challenges we currently face in forecasting these tail events in the long term. And I'll finish with some of the opportunities that we have for forecasting these tail events better. So just a high-level overview of REsurety. We are a software and services company, and we provide data-driven insights to buyers, sellers, investors of clean energy to help them meet their financial and sustainability goals. And one of the key pieces of information we provide is estimates of the future value of wind and solar projects. And in order to do that, we need to have some take on what the future price of power is going to be. So how do we do that? We use a fundamentals-based price forecasting approach. We produce long-term 20-year price forecasts for all the deregulated markets in the US. And these forecasts reflect 40 years of weather variability. So we start with the input meteorology, the wind and solar modeling, and the power markets fundamentals outlooks. We put them into a production cost model called PSO, which is developed by Analytics. And then what we get is long-term price forecasts that incorporate both weather variability and fundamentals variability. And that's what underlies all of our software products and our services. So I'll start by talking about how extreme weather impacts power prices. So I think we're pretty familiar with how extreme weather is going to impact the demand side of things. When you have really cold or really warm temperatures, that's going to drive up demand, and that's going to drive up the price of electricity. But weather also impacts the generation side, and particularly in markets that have high renewable penetration, there's a really high impact of what that generation is to the price of power. And that's because all of these renewable generators are very low cost. So when there's a lot of renewable generation, that's going to tend to drive down the price of electricity. When you don't have that renewable generation, you're having to reach further into your supply stack, bring on those more expensive generators. That's going to drive up the price of electricity. And this is exemplified in this figure on the right here from the EIA. So these are simulated hourly ERCOT electricity prices on a summer day according to different scenarios. So the base case is this goldenrod line in the background here. So this is kind of typical demand, typical renewable generation. So you probably get a little bit of a price spike in the mid to late afternoon, but nothing too substantial. Once you start to dial down your renewable generation and get into this low wind case in the middle here, that's when you start to get these higher prices. And then when you have this double whammy of high demand, low renewable generation, that's often when you get these really extreme prices. And that's shown in the extreme case in this dark blue line here. And if you look back at monthly average power prices in ERCOT over the last decade or so, it's pretty easy to pick out when they've experienced extreme weather events. So this first circle I've indicated here was the August 2011 heat wave. That was actually the hottest summer on record in the state of Texas. Another heat wave in 2019. Winter Storm Uri in February 2021 is off the charts here. I need Al Gore's moving platform from Inconvenient Truth to show just how high those prices were. There was a heat wave in summer of 2022, and then a pretty significant heat dome event last summer. And I'll note that most of these examples are during the summer months, but Winter Storm Uri showed that extreme prices are not unprecedented in the winter months as well. And of course, these extreme prices are not just limited to ERCOT. So these are some examples from a hub in PJM. So you can see the infamous 2014 polar vortex, some cold snaps in 2015 and 2018, and then December 2022, Winter Storm Elliott. So contrast to ERCOT, Northeast markets tend to see these extreme prices during the winter months, but it's definitely not unprecedented to see high prices during the summer months as well, particularly as we have a more weather-dependent generation stack. Okay, so we've seen how extreme weather impacts power prices. So what are some of the challenges we face in trying to forecast these events? So I'm going to break this into 3 different categories. So first, the weather data inputs, second, the grid condition inputs, and then third, the model that we're using itself. So on the weather side, it's getting really hard to figure out what is actually a tail weather event versus what is just the new normal. What we kind of try to do to incorporate as much weather variability as possible is we use these long-term weather models, these reanalysis data sets. But as both Jared and Justin have mentioned, the resolution is pretty coarse, so it's hard to use them to really estimate the variability in renewable resource. Moving on to the grid side, as we've been talking about all week, the grid is rapidly changing. So even if we've seen extreme weather events in the past, we've never seen them in a grid that has this much demand and this much renewable generation. So we just don't have a precedent for what this is going to look like. And then in that demand and renewable build out, there's a lot of uncertainty right now. And then finally, we're putting all this information into what is just a model. And those models can't capture everything. And they can't capture that perfect storm of events that can often lead to these really high price cases. So starting on the weather side. So summer of 2023 in Texas was the second hottest summer on record, second only to 2011. And that sounds like it's a tail event. But then when you look at this figure from the Texas Tribune, you realize that it is kind of becoming part of the new normal. So this figure here shows the average summer temperature over the last 40 years in Texas. And all of the red circles are summers where the temperature was above the 20th century average. And the blue circles are summers where it's below that 20th century average. So if you zoom in on this shaded area, which is the last 20, 23 years, you're not seeing a lot of blue circles. Almost everything has been above average, which really brings into question what is average anymore? And are we going to see more of these really hot summers? And it's really challenging to figure out how hot they're going to be and how frequent they're going to be. So one thing we do in the price forecasting space is we try to incorporate as much weather variability as possible. And the main data sets for doing that are these reanalysis data sets like ERA5 and MIRA2. But as we've talked about earlier this week, their spatial resolution makes it really challenging to capture the impacts of weather on renewable generation. And just to show what that looks like, this plot here shows the observed generation for an ERCOT North Solar project from last summer. So the black line is the actual generation from that project. The blue line is the generation modeled using ERA5 as an input. And on the bottom here, just to show that this is a very impactful week, this is the ERCOT North real-time power price. So several days where prices exceeded $1,000 per megawatt hour. So if you zoom in on a few days, you can see that on the sunny days where you have that typical solar generation profile, ERA5 can depict the generation pretty accurately because it's not all that hard to model solar generation when you don't have any clouds. On these days when we start to deviate from that profile, when we're starting to get cloud cover, this is where the coarse resolution is really becoming a challenge. ERA5 has 30-kilometer resolution. Clouds occur on a smaller resolution than that. So you can see this generation in the observed decrease because of cloud cover, and ERA5 just isn't capturing that in a lot of cases. In some cases, it's overdoing the cloud cover, and it's actually underestimating generation. And these sudden ramps in solar generation are really impactful, especially in markets that are relying on this solar in the middle of the day. So what we've seen in ERCOT the last couple of years is these high price events shifting from the afternoon to the evening ramp because of the influx of solar. But when you turn down that solar generation suddenly in the middle of the day, then you're losing that cheap generation and those prices can get high again. And we actually saw during this week some days that had double price spikes. You had a price spike in the mid to late afternoon and then another one during the evening ramp. And if your data set can't capture these types of solar ramp events, you're not going to be able to capture the frequency of these extreme prices. And just to show how increasing the spatial resolution really helps with cloud cover, this is that same project modeled using a high resolution data set. But the problem we face with the high resolution data sets is that they don't have a very long historical record. So they're great for the last 5 to 10 years, but they're not going to extend back 40 years in time. And that's why it's so important to have both the high spatial resolution and the long record length if we really want to capture what the actual weather variability was. So moving on to the grid side, we really just don't have a precedent for what the grid is continuing to look like. So as an example of that, last year, ERCOT set a new peak demand record of over 85 gigawatts. This was a 7% increase from the year before. And then 2011, which was actually the hottest summer on record in Texas, was only ranked number 7. And that just shows how much demand growth has occurred in the last 10 to 15 years. And as we've talked about a lot this week, that demand is expected to only increase. I won't talk too much about the data centers. That's one of the hot topics this week. But the data center growth presents a real challenge for trying to forecast what the grid composition is going to look like. There's a lot of questions about how the grid is going to serve that load. So can we serve it with the existing planned resources? There have already been reports of fossil fuel generators delaying retirements to try to serve these resources. So there's a lot of questions about how we're going to serve this unprecedented demand. Also questions about what the shape of that demand is going to look like. Are we going to see an increase in peak demand? Are these data centers going to be following incentives to operate when prices are low or when the grid is cleaner? Lots of open questions about what exactly that's going to look like. On the supply side, we're in an area where getting the supply right is really tricky. So this figure shows the actual solar additions in ERCOT and the planned solar additions. So the kind of teal bars here show the cumulative operational solar in ERCOT by the end of each year going out to 2026. And then the maroon and green lines are solar projects that have an interconnection agreement signed. So it's a little hard to see the small numbers here, but ERCOT's expecting basically a doubling of solar capacity in the next 3 to 4 years up to 50 gigawatts. That is a huge amount of solar. But there's a lot of uncertainty on how much of that solar will actually get built and when it's going to come online. There's been a lot of supply chain issues. In the next couple of slides, I'm going to show just the impact of that supply chain uncertainty on forecasting the price of power. So at the start of 2023, ERCOT solar capacity was forecasted to exceed 18 gigawatts, with most of that capacity coming online prior to the summer to help with the summer peaks. So what actually happened was that the maximum solar output last summer in ERCOT was closer to 14 gigawatts, about a 4 gigawatt difference. So how does that impact our forecasts on the price of power? So this figure shows our range of forecasted prices for ERCOT West in August 2023 if we assumed that 18 gigawatts of solar all came online prior to the summer. So this blue bar here shows the range of prices that came out of our forecast, and each of the green lines shows the realization from individual weather scenarios. So what you can see is that there are some high prices here, but the actual outcome, which was close to $200 per megawatt hour, is pretty far outside of that distribution. So we would have predicted that what actually happened just wasn't possible with that amount of solar capacity. Once we dial down that solar capacity to 14 gigawatts, which is what actually happened, the tail of that distribution increases pretty significantly. And we're seeing an increased probability of those high price events. And now the actual outcome is within our distribution. And one interesting thing I wanted to point out is that the highest price in our distribution was if we assumed August 2011 weather happened in the grid of 2023. So even with the effects of climate change, there is a lot of value in looking at the historical record and taking all of this historical weather, putting it into the grid of the future to see what different possible outcomes could look like. So finally, fundamentals models can't capture everything. So I thought this figure was really interesting. This shows US natural gas production over the last couple of years. And you can see the impacts of these winter storms. So Winter Storm Uri, Elliott, and Winter Storm Heather. And these types of widespread events are really hard to capture in the model. How this widespread cold weather impacts both natural gas production and also transportation. A couple other examples. How effective demand response programs are going to be. Those are really important during these high demand days, but there's a human element there. You can ask your residential and commercial customers to turn off the thermostat, reduce their electricity use, but it's up to each individual's decision oftentimes to actually do that. Another thing that's really hard to capture is forced outages or unplanned outages. So there's no denying that when you have extreme weather, you're probably going to have more outages, especially during these cold weather events. But figuring out exactly how many outages you're going to have, how long these generators are going to be offline is really challenging. And that's definitely going to impact the frequency of these tail events. So finally, I'll finish with some opportunities for forecasting tail events. So one thing that's more important than ever is to incorporate weather variability into forecasts. My catchphrase is friends don't let friends use 8760s, particularly for price forecasting, and I mean it. And just to show why that's so important, this plot here shows forecasted hourly prices for a June day in ERCOT in 2030. So if you use a typical weather year, that's the black line there. So you get a little bit of a peak in the late afternoon, early evening, nothing too substantial, but all of these thinner colored lines are individual weather outcomes. So once you start to increase the variability, that's when you're starting to see the possibility of these tail events. And you just have no chance of capturing tail events if you're only using a typical weather year. It's also really important to incorporate fundamentals variability into forecasts. So what are different possibilities for what the grid composition could look like? So this plot here shows solar capture rate according to different fundamentals scenarios. If you're not familiar, solar capture rate is basically the percentage of the average price of power that a solar project can capture. So each of these different colors is a different fundamental scenario. The solid line is the average across all of our different weather years, and then the light lines are the individual weather year outcomes. One thing we found really interesting is that the sensitivity of prices to weather conditions really depends on the grid composition. So in our high storage case, where we're putting a lot of storage on the system, that really tends to smooth out these high prices because you're basically able to time shift your energy to times of day when it's needed. So there's not a ton of weather variability once you add a ton of storage. In contrast, in a net zero scenario where we're trying to reach net zero by 2050, you see a lot of weather variability because you're adding so many renewables to the system. And it's really important to capture what this range of outcomes could look like, because we just don't know exactly what the grid composition is going to look like 10, 20 years in the future. And then finally, it's really important to account for how extreme weather doesn't just impact the demand side of things, but also the renewable side of things. Because oftentimes these weather events that lead to extremes in demand can have adverse impacts on renewable generation. One really good example of that is the weather event that happened during Winter Storm Uri. So this is a sea level pressure map. And we often see this type of setup when we have these really cold air intrusions. You have cold air building up at the surface, so you get this really deep, high pressure system. And those systems tend to be very stagnant. You're not getting a lot of wind generation. And this is during a time of year when wind generation tends to be pretty high in the Midwest and the South. So you're getting this double whammy of high demand, low renewable generation. And this type of event was definitely not unprecedented in ERCOT. This is a very similar setup in December 1983. This was back in the good old days before the Weather Channel started naming winter storms, so we just call it Arctic outbreak. But again, high pressure system, low wind generation, and this is where having that historical weather period is really impactful. But it is really important to look at how not just the magnitude of these events, but also the frequency of them is going to change in the future. Because even if we've seen them in the past, we don't know how likely they're going to be in the future. So just to sum up, when we're talking about forecasting the price of power, our two really key inputs are demand and supply. And there's a lot of uncertainty in those two components right now. So with a grid that's increasingly impacted by the weather on both the demand side and the supply side, it's really important to incorporate both the weather variability and also the fundamentals variability so you can try to capture these tail events. Thank you.